Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about stopping criteria and pruning. In the end, you should understand which problems arise when we grow the tree until the end. You should know different stopping criteria, and you shall understand the general idea of pruning. If we follow the recursive partitioning procedure used to grow a card, then this procedure could run until every leaf only contains a single observation. The problem here is that very complex trees will overfit to the training data. So this means they fit the training data very well, but they do not generalize on new unseen test data. So at some point we should stop splitting nodes into ever smaller child nodes to overcome this overfitting problem. So here you see an overfitting tree. So for example, if you look at this observation here, it has a unique, this is a leaf with just one value, so the optimal constant in that node will just be exactly the value of the target value of this observation. And of course this overfits very badly. So we can reduce overfitting to some extent with a less deep tree. So if we just stop earlier than growing until the end. There are different stopping criteria. Some examples here are: don't split a node if a certain number of leaves is reached. So this would mean that beforehand we set a number of leaves that the tree should have. For example, 100 leaves, and if we have split so far that the tree is large enough and has 100 leaves, then we just stop. Another criteria could be: don't split a node if it contains too few observations. So just split a node if it has more than, let's say, 5 observations. Or don't split a node if the splitting results in children with too few observations. Or don't split a node if splitting does not achieve a certain minimal improvement of the risk in the children compared to the risk in the parent node. Okay, so the risk in the children will never be worse than in the parent node, but perhaps the improvement is just very minimal or not there at all. And then we could say we define a threshold, and if the improvement is lower than this threshold, then we do not split there. And finally, don't split a node if it already has the same target value. So if the node is pure, or if all the observations have identical feature values, because then we cannot win anything by splitting further. The selection of a stopping criterion and setting of concrete values. So with concrete values we mean, for example, the number of leaves we want to reach. These values are hyperparameters of cards and can be chosen via tuning. Another problem is the horizon effect. It is hard to tell where we should stop while we are growing the tree. Before we have actually tried all possible additional splits further down the branch, we can't know whether any of them will be able to reduce the risk by a lot. Okay, so just by doing the splits, we will see if the risk improves. And if we don't do the splits, we also don't know how much we could win by doing those splits. So here, for example, we have on the x-axis the depth of the tree, on the y-axis the training loss, and of course the training loss goes down as the tree grows deeper and deeper, which eventually will end in some overfitting. But if we, for example, are at depth 8, we have no idea how the training loss will behave for deeper trees than depth equals 8. So we have to try it out to see what happens there. But then perhaps we are in overfitting, and well, that's where pruning comes in, because then the idea is to basically go back if we overfit. So pruning is a method to select the optimal size of a tree, and we want to tackle the horizon effect with this pruning method. We could do something like pre-pruning, which is finding a combination of suitable strict stopping criteria via tuning, for example. The alternative, so what I told you on the stopping criteria slide, okay, we have a very large set of different stopping criteria. We could just try out everything via tuning, and see which stopping criterion performs best. As an alternative to that, or perhaps as an addition, we could grow a very large tree and then remove branches post hoc, so that the resulting smaller tree has a lower risk. And this is then called post-pruning, and often post-pruning is meant when referring just to pruning, and we will also mean post-pruning if we say pruning. How does that work? We give you an example of the most prominent pruning method, I guess, which is called cost complexity pruning. The idea, again, is to grow a large tree and then post hoc to remove the least informative leaves or branches. In CCP, we have a regularization parameter alpha, which penalizes the number of leaves in a subtree. So we have this regularized risk here of a subtree T. Let's see what that formula tries to tell us. We have the complete tree T0, and all those subtrees will be, well, subtrees of that complete tree. Okay, and then for the regularized risk here, we sum up the losses of all those observations in the subtree, and then we add as penalization the product of the penalization parameter alpha and the number of leaves of the subtree T. Okay, so T is a subtree of T0. So the more leaves we have, the higher is the regularized risk. Okay? Keep in mind, we want to have a small regularized risk. So if the first term here doesn't change, but also let's say we compare two subtrees, both have the same sum of losses, but one subtree is larger than the other subtree, so has more leaves, then we prefer the smaller tree of those two trees. And just that you get the formula here, we sum in those inner sum over all the observations where the feature value of this observation is inside that rectangle that relates to the subset of the feature space of this terminal node or of this leaf. And Cm is the optimal constant prediction in that leaf, and then we sum in the end over all the leaves. What CCP does is performing a greedy backward search. What means that? So we compute the regularized risk with a fixed alpha for all possible subtrees that can be created by replacing one internal node with a leaf. So we have to set alpha fix beforehand, then alpha is a hyperparameter, and using this hyperparameter alpha, we compute the regularized risk for the subtree. By replacing a node, we also eliminate all the subsequent nodes. Okay, so we cut down everything which comes after this internal node. And then, in the end, we select the subtree with the lowest regularized risk, and then we repeat the procedure. So that's why it's called greedy. So we do it again and again and again, and we stop if pruning does not further reduce the risk. And I give you an example on the next slide. Okay, that's the idea of CCP. There is a proof that this results in the pruned tree with the lowest risk, so which is good news, because when doing greedy optimization, we could always end up in some local optimum. But in this case, actually with this algorithm, we get the global optimum, of course, given or conditioned on the starting tree, on the complete tree T0. If we set alpha to 0, then we would obviously select T0 because the risk will not get better by cutting away any branches, but the regularized risk might. And then alpha, which is a hyperparameter, is typically selected via cross-validation, but of course you could also use other resampling strategies. Other post-pruning methods include the reduced error pruning or the pessimistic error pruning. So let's have a look at an example of CCP. We have this full tree here, and the risk of this full tree is 16.82. Okay, the full tree has 1, 2, 3, 4, 5 leaves, and perhaps with a different color, 1, 2, 3, 4 internal nodes. And pruning means that we iteratively replace those internal nodes by leaves. So we look at those 4 internal nodes here and replace them by leaves, so not splitting any further. And then we can compute the risk, the regularized risk, which results by doing this, so by replacing the internal nodes by leaves. So for example, here on the right hand side, if we replace this internal node by a leaf, then we just cut away this and that, and here, perhaps a little bit small, is the resulting regularized risk by pruning those 2 nodes here, those leaves. And we do the same thing for all the 4 internal nodes, and it turns out that the best risk improvement is by cutting away those 2 leaf nodes here, because this results in a risk of 16.78. So this is the tree after replacing this internal node by a leaf, and well, this is then the risk or the regularized risk of the subtree. And now we can go on and have a look at again what happens if we replace these 3 internal nodes by leaves. And well, we already know what happens here because we computed that before, but here on the right hand side it could happen something different. And then we see, okay, we can prune the left hand side and get a risk of 18.4 if we do that, but recall that before we had a risk of 16.78, so the risk went up, which is bad, which means that we do not prune further here. Okay, so the final tree will be this one. Okay, so the slides that come after that is just to show you what would happen if we would proceed with this algorithm. So we would again try out what happens if we replace those 2 internal nodes by leaves, and see, okay, risk goes up, and do the same thing once again. And then we have just a root node, which is a really easy tree with just all the observations in the same node and just having one constant prediction, which is equal for all the observations, and the risk goes considerably up. So of course that's not the optimal tree. And just to make sure, again, this would be the optimal pruned tree because it has the best regularized risk after the pruning.